Okay, well, thanks everyone in person, online for joining. So this is the Live Data Science Seminar Series, kicking off for the 2023-2024 calendar year. And we're very happy today to have Dr. Saskia Charity joining us live and in person. So normally these seminars are online, but today we're in person, which is really nice. So Saskia, I'm just going to go through a little bit of her backstory. So she got her master's degree at the University of York, where she studied physics and philosophy. She then came to Liverpool to do her PhD, working on track reconstruction algorithms for the g-2 experiment. She then flew abroad to Fermilab, where she was working within the Muon department as a postdoc, before fate dragged her back to Liverpool again. She's now a senior research associate in the particle physics cluster, working on the g-2 and the mu2e experiment. She's the research coordinator for the magnetic field analysis team group research effort,
yes.
G-2. So thanks very much for joining us today. Without further ado, I'll leave it over to you.
Oh, thank you for the introduction. That was very nice. Okay, so I will share presentation. Okay, hopefully that looks okay, but let me know if there's a problem. So yeah, thank you so much for the introduction and for the invitation. It's always very nice to talk about the g-2 experiment. So today I'm going to try and cover a lot of information, but not overwhelm you with too much information. Talking about the g-2 experiment, the recent result that we had, and trying to focus a bit on the sort of computing challenges within the experiment, which might be relevant for people who are interested in big data, but don't necessarily know that much about the g-2. But I will begin with a bit of background and a little bit of physics theory just to motivate the experiment and understand why we want to measure this number with such extraordinary precision and why we require such difficult computing to do that. Okay, so I'll start with a bit of background. So what is the g-2 experiment? What are we trying to measure and why? I'll talk about how we measure the quantity of interest, some of the detectors and the hardware, and some of the computing challenges associated with collecting the data. Then I'll talk about the challenges associated with reconstructing and processing all of the data that we collect and how we perform the analysis for the final number. So just to introduce you, this is the Muon g-2 collaboration. We're composed of 181 collaborators, approximately, over 33 institutions in 7 different countries. So here's Liverpool down here, and here's a picture of the collaboration in 2019, when we were very lucky to be able to go to Elba for a collaboration meeting, which is in Italy, so that was rather nice. Recently, if you were here in the summer, you might have seen a lot of Americans walking around excitedly whispering to each other, and it's because we had the g-2 Physics Week here in Liverpool. So actually over in the Spine, which is a very nice building over there, we held this unblinding ceremony where we looked at the data, removed the blinding offsets from our data for the first time, and knew our result that I'll tell you about today. So it was really nice that Liverpool was the host for this big ceremony that we had, and then we announced our result on August the 10th. So I'll tell you a bit about what that result was and why it was so exciting. Okay, so starting at the beginning, let's talk about the standard model of particle physics and where muons fit into that. So if you're not familiar with particle physics, everything that we know about is comprised of these particles in the universe, and the muon is one of these. So this is a second generation lepton, which is similar to an electron, but differs in some quite crucial ways. So one of those ways is that it's 200 times more massive than an electron, and the other way is that it's unstable. So it decays after 2.2 microseconds to an electron and 2 neutrinos. So this means that we can do some rather interesting experiments with muons that we can't do with electrons. So in this sense, it's kind of a bit of a Goldilocks particle, because while coupling to the interesting physics that we want to probe scales with mass, that might tell you that you would like to look at taus, which are heavier again than muons. These are very short-lived, and they also decay hadronically, so that can have very complicated things to analyze. So the muons kind of sits in this nice state where it's quite clean to analyze, but it couples to all of the interesting physics that we want to probe, and it stays around long enough that we can actually look at it. And then what you're going to hear a lot about today is that it's got a property called spin, which rotates in a magnetic field. So if you remember nothing else about g-2, remember that we're looking at the spin of a muon rotating in a magnetic field, just like this. So if you have a vertically aligned magnetic field and you have a muon inside, then its spin vector is going to precess about the direction of that magnetic field vector, just like a spinning top trying to spin around on a table. And the rate of this, this precession is determined by this quantity g, which is a dimensionless number that just parameterizes the relationship between the muon spin and the external magnetic field. So when you have this magnetic moment in a magnetic field, you're going to produce a torque, and then magnetic moment mu is defined by this quantity here, which is proportional to the spin of the particle and the quantity g. So without going into too much detail about all of this, basically Dirac predicted that g should be exactly 2 for a spin half fermion, but we know from measurements and things like that that the first time that we tried to measure g of the muon, it was actually done for a different fermion, we measured that g was greater than 2. And now, sort of several decades later, we understand that the reason for this difference from 2 is that the muon can couple to virtual particles in the vacuum. So instead of just living on its own, muons will interact with different particles that can pop in and out of the vacuum for a very short amount of time. These will screen the interaction of the muon with the magnetic field. So they basically just get in the way. So I kind of like to think about it like if you've got a fridge magnet and you keep adding extra pieces of paper behind the magnet, it's going to feel that force more weakly and eventually it'll fall off. So these extra particles are kind of like extra pieces of paper between the muon and the magnetic field. And we're interested in measuring those virtual particles. So that's why we designed an experiment where we can try and see exactly which particles are getting in the way of the interaction between the muon and the magnetic field. So this is the way that it would happen. If you're used to looking at Feynman diagrams, you could have particles entering in loops here, and we're interested in what these particles in this loop are. So I won't go over the maths of all of these contributions, but just to show you, the interesting thing about the muon is that it's sensitive to all of standard model physics at some level. So in the purely Dirac sense, we would just have this tree diagram. By far the largest contribution is the QED contributions, which are diagrams like this. It's sensitive to electroweak interactions, and these two terms represent hadronic interactions. So you don't worry about all of the detail. The key thing about this is that this is the largest one, and these contribute the largest part of the uncertainty because they're very difficult to calculate. So if you followed any of the news about the g-2 experiment over the summer, you probably heard people talking about hadronic corrections because these are the parts of the theory that are really difficult to calculate. And lots of our colleagues over in the maths department in Liverpool here are heavily involved in the effort to calculate this standard model prediction. So there are multiple ways of doing this. It's an international effort of loads of different theorists all over the world. And if you're interested in how they make this prediction, you can read this very long paper, 166 pages, but it's very interesting. So go and have a look if you like standard model theory. Okay, so just again to show you, so if you just had no virtual interactions, then you would just have this G. So G of the muon is equal to just 2 here. And then the largest part is the QED. And then this pie chart is just to show that despite only accounting for a very small amount of the value, the HVB terms dominate the size of the uncertainty. So that's really the terms that we need to, that the theorists in Liverpool and elsewhere in the world are really interested in measuring, is reducing this uncertainty on these hadronic vacuum polarization terms. Okay, so everything we're interested in is these loop terms, so all the bits that are different from 2, which is why the experiment's called g-2, and we define this quantity A mu, where A stands for anomaly or anomalous magnetic moment, which is the difference from 2 of G. So what we can do is we can combine our measurement with the standard model prediction, which includes everything that we know about in the standard model. And if the prediction and the measurement are different, then this could be a sign of new physics because some other particle was causing an interaction that the standard model hadn't accounted for. So the most recent g-2 result was announced at Fermilab on August the 10th, after we've been carrying around the secret for a couple of weeks, unblinding the result here at Liverpool. The thing that made us really excited about the measurement is that it agreed really well with our previous measurement that we announced in 2021. And the thing that made us excited about that one is that it agreed really well with the previous measurement at the Brookhaven experiment 20 years ago. So repeating experiments lots of times gives you confidence that you're doing the right thing. So we were happy that when we analysed a lot more data, it showed that we nothing new had cropped up, and this sort of statistical fluctuation had meant that we changed a lot from our previous value and things like that. So the reason that there was some attention worldwide about this value is that previously, going back a couple of years, if you compared the Fermilab result with the standard model prediction, this currently accepted measurement in the white paper that I directed you to, you saw quite a significant difference, which got everyone excited that there might be new physics lurking in the muon sector that was affecting the magnetic moment here. The picture now is a little more complicated, and I won't go into all the theoretical details in this data science talk, but just to give you a bit of context, what's happened since is that the standard model computation, the way that you can do this prediction, there's a lot of novel methods in the theoretical community to try and do this prediction. So traditionally, you use the data-driven method by summing up lots of different contributions from E plus E minus colliders and trying to do your prediction that way, because it's very difficult to analytically calculate and it would be very, very computationally intensive. But recently, there was an announced result from the BMW lattice collaboration who do these lattice QCD predictions. So these are really, really computationally intensive calculations where you basically have to simulate loads of different paths, and it's really, really, you know, hugely computationally expensive. And currently their result looks to agree a lot better with the Fermilab experiment's result. So they haven't updated this consensus prediction just yet because they're waiting for other lattice groups to evaluate the same number, because currently only one collaboration has managed to do it at that full level. And then there's been other sort of complications, which have been other E plus E minus results for the prediction, sort of looking a bit different from previous E plus E minus results from other experiments. So there's a whole host of things that we could talk about maybe later in the pub, or look at, I can recommend some papers for you. It's a really interesting hot topic in theoretical standard model physics at the moment, is working out what exactly this prediction is. Because obviously if this prediction stays strong, then we've got a really exciting discrepancy on our hands. If we have to update the standard model prediction because of these other changes, that's going to have some sort of consequences for the rest of the standard model. So it's something that really needs to be understood, but we can't quite get really excited just yet, but we can get excited because we've made a very difficult, precise measurement, which is all that we care about in experimental particle physics. Okay, so now I'll talk about the experiment. So this is an aerial view of the accelerator complex at Fermilab. So we've got a big recycler ring. So we enter protons from the accelerator complex at Fermilab, go around this big recycler ring here, where they're bunched into groups of protons, so that they're not all arriving in a continuous stream, but we have bunched proton beam. These are directed into a pion production target just here. So the protons collide with a target and produce pions. Something that was a really interesting innovation for this experiment, as opposed to previous incarnations of the g-2 experiment, is that we then send the pions around something called a delivery ring. So this means that there's time for all of the pions to decay into muons before we inject them into our experiment. So previously, sometimes you would have g-2 experiments in the 90s and before, where they were injecting pions as well as muons into the beam. But now we can make sure that all the pions have decayed to muons and inject a really clean beam. So I don't want to go over too many details, but these are kind of relevant for some of the data rate calculations later on in the talk. The beam arrives in 120 nanosecond wide bunches, and all of the muons in the experiment are at this 3.09 GeV value over the small spread. So this is what the sort of bunches look like that are injected into the experiment. And here's a plot showing the time distribution of the injected muons. So ideally, you'd inject all your muons at the same time, but in practice, if you know anything about accelerator physics, it's very difficult to do that. So there's some time spread of the injected beam as well, but we try and keep it less than 120 nanoseconds. Okay, so this deliberately complicated slide that I won't go over everything on is just to show you all of the many different systems that we have to use in order to do this complicated measurement. So we inject the beam of muons here. This storage ring magnet is 14 meters in diameter. Just to give a bit of scale, there's a person standing in the middle there. I think it's Matt. I think it's someone called Matt. So we inject muons into the storage ring here, and we try and keep them in this magnet for as long as we can. So to do that, well, there are many different devices, such as kicker magnets and electrostatic quadrupoles that squeeze the beam and kick it and move it about to try and keep it in there. And then we have to do things like measure the magnetic field all the time to make sure that it's not changing. And we have to measure the beam distribution within the magnet to see exactly where the muons are. So we can't just inject them and measure them later. We need to know exactly what the spatial distribution of them is. So this is just to give you a snapshot. It's not just people talk about us measuring one number in this experiment, but I can think of about 100 off the top of my head that we have to always be taking account of. Okay, so as I said, we inject the 3.1 GeV muon beam into the storage ring where they circulate here. If you took a slice through the magnet this is what you would see. So this is a cross section of the magnets here. This is the there is coils here and coils here, and this is the direction of the field lines within that magnet. So it's all designed such that the magnetic field in this region where the muon circulates is as vertical as we can possibly make it. This is all I'm going to really say about the magnet here, which is a bit sad because it's about 5 years of my work to make plots like this one, but ask me about it afterwards. So it's really, really challenging to make sure that the gradients of the magnetic field are not too high in this region. So you want as vertical a magnetic field as you can have, because this defines the axis of rotation for the muon spin here. So if it was changing around a lot, you wouldn't, you'd have a complicated measurement. So we have to really control the non-vertical terms in this magnetic field at a very high level. Okay, so this is a top-down cartoon of the muon storage ring. So this would be where the muons circulate. And in this animation, the blue arrow here is the momentum vector. So if you just follow the blue arrow around the circle, you can see the direction of the muons going around and around the storage ring. So this vector just points along the center of the storage ring, and you can see the momentum vector going round and round. But what's happening as well as the momentum processing, the momentum orbiting there, the spin is going to be processing about this vector as well. So they both process, and as you can see, the spin rotates ahead of the momentum as the muon is orbiting the ring. So there's a difference between the frequency of the spin rotation and the frequency of the momentum rotation. And this is a really important difference, that these two frequencies are different. If they were the same, that would be the case where G is equal to 2. So any difference in these two frequencies directly tells you how different G is from 2. So this is how we measure G minus 2. So you can see here, this arrow rotating there is the difference frequency. So we call this omega A for omega anomaly, which is just the difference between the spin frequency and the cyclotron frequency. So this is how the signal of the experiment is the rate of precession of this pale red slowly rotating vector here. Okay, so don't worry too much about that, but let's think about how we measure it. So what we need to do is measure omega A, which is this difference frequency. We need to measure the magnetic field B, and both of those measurements will enable us to extract A mu, which as we saw is G minus 2 over 2. So just by measuring that frequency and the magnetic field, we can extract this value. But I'm afraid that's not the end of the talk. So how do we do this then? So the muons are going around this ring. They're orbiting several thousand times before they decay to positrons, which have got a lower momentum, so they spiral into the center of the magnet. So the way that we design the experiment is to furnish the inside with 24 electromagnetic calorimeters, which will measure the energy and the arrival time of these decay positrons coming from these muons. So we don't measure the muons directly, we measure the decay products, and by counting those, we can tell what the muon was doing. So again, a little bit more physics for you. If you're interested in parity violation in the weak decay, you can read the text on the left-hand side. And if you just want the quick summary, we've got this video on the right here. So the crucial thing that enables this experiment to be possible is that the highest energy positrons are preferentially emitted in the direction of the muon spin. So the way that the muon is pointing, the higher energy ones, you're going to have the highest level of correlation with the spin. So here, what we do is we apply a threshold energy, and we just count the number of positrons emitted above that threshold energy. So you can see that when the spin is pointing in the direction of the momentum, this part is higher, and when it's pointing away, this part is lower. So spin parallel to momentum, you get a high number here, spin anti-parallel to momentum, low number here. So this is all because of parity violation, but it just means that just by counting the number of positrons above a given energy, we can measure an oscillation which is directly proportional to the anomaly frequency. So here's what the data looks like, and this is actually real data taken from one of the runs in 2021. So again, by counting the number of high energy positrons above a threshold as a function of time, we can directly measure this frequency. So here again is the spin going around, and when it's parallel to the momentum, we have more positrons above the threshold energy, and when it's anti-parallel, we have less positrons above the threshold energy. So this is just how we make this plot, is just by counting these number of positrons. And to make a really precise measurement, we have to count many, many billions of these. But this is just the principle of how we make this plot. So if you've seen any of the G-2 papers, you might have heard people talking about a wiggle plot. this is why we call it a wiggle plot, because it's nice and wiggly. So here's some more data. So this is the data in the g-2 experiment accumulating over the period of 1 hour. So you can see that even after just 5 or 10 minutes, we've already got a clear oscillation here. So it was really cool to be part of the experiment when we first turned it on, because in some experiments you sometimes have, like, you're waiting for a collision and see some hits in your detector. This one was kind of weird because we just had to sort of wait for a plot to emerge. So we were like seeing noise in the detectors and thinking, is anything, like, are we doing the right thing? And then eventually when we had enough statistics, we could see this wiggle. So it was really nice, but kind of, you think it's going to be one moment, but it was more like several minutes tuning things up to try and get this. But okay, so what we have here is a sinusoidal oscillation decaying exponentially. So we can fit this function just with 5 parameters, where 2 of the parameters are associated with the exponential decay, and 3 of the parameters are associated with this oscillation. So this is like a wrapped exponential plot. So just otherwise we'd have a really, really long plot going off the screen. We wrap it back around. So after 500 microseconds, most of the muons in the ring have decayed, which is why there's these large error bars on these points at the bottom here. And at the top, we've got the most muons still in the ring. So we've got nice clean oscillation there. And the whole purpose is to try and fit this 5 parameter function to this data and extract this precession frequency omega A. It's a little bit more complicated than that. So what we have is our calorimeters that I mentioned before, 24 calorimeters lining the inside of the ring. These are arranged in a 6x9 array of lead fluoride crystals. And what happens is that when one of the decay positrons enters one of these crystals, they cause a particle shower and emit Cherenkov light. So this is the light inside the calorimeters. Unfortunately, we don't see this because for it to work, they have to be in light tight boxes. Otherwise, it would be really cool to have all this glowing stuff all over the place. But okay, they're all sealed off. But the particles, so the positrons enter the crystals, emit light, which is picked up by some detectors called silicon photomultipliers. So they just count the amount of light released in each crystal when the positron arrives. And this, so in this grid here, this shows all the crystals, and you can see one of the pulses of a particle arriving in that crystal. So the first part of the analysis is just to reconstruct the energy that was deposited by the incoming positron by fitting this pulse. So we digitize the signal and then fit it with some template functions and extract the positron time and energy from the fit. So this is a fit to a typical pulse, and we can get the time and the energy of that pulse. So this is a pretty complicated part of the analysis, and it's really crucial because we're doing a precision experiment and we need to know how many positrons as a function of time. If you had like a bias and you were artificially counting them, or if it was a bias that was changing over time or something, then you might directly change your signal that you were measuring. So it's really important to get this reconstruction correct. So in this plot here, you can kind of see the 6x9 crystals. And this shows you the position when a positron enters the detector and deposits its energy. So it doesn't always put all of its energy in the one crystal that it hits. It could share some of its energy around neighboring crystals. So the reconstruction algorithms have to sort of figure out which crystal was hit when you have energy in neighboring crystals. There are other effects which I won't go into all the details, but something called pile-up is a large systematic for this analysis, which is where you get 2 electrons that arrive in the detector close together in time. And sometimes if they're really close together in time and space, they would look like one pulse, one high energy positron, but really they were 2 low energy positrons arriving in the detector. So it's important to try and minimize this pile up by having really good timing resolution, basically, and then doing something else to try and tease this out. So I am not an expert in machine learning, but I just wanted to share a link to this poster to some collaborators on g-2 from Shanghai who are currently working on a machine learning model for doing this reconstruction. So I'm not an expert in this part. I know that currently there is no machine learning done, but in the current analysis, they're looking for other ways to sort of cross-check the existing methods. And this is, you can kind of tell that this is the kind of analysis that might be useful to do a machine learning-based analysis, because it's kind of like pattern recognition. You can do certain things using lots of data to train it and try and find similar ones. So I really put this in as just a sort of literature further reading. If you're interested, go and find this paper to try and see how novel techniques they're trying to use machine learning to identify the pulses in the calorimeter. Okay, so the other detector system that we have that I'm very fond of is the tracking detectors. These were assembled here at Liverpool, and you can tell that because I think the University of Liverpool logo appears on them something like 20 times per module. So very proud of them. These are assembled in the clean rooms downstairs. Here is a picture of me and Dominica, who's another postdoc here at Liverpool. This was back in 2014, I think. So it's been a long journey for these detectors. What we have is 2 locations around the ring. There are 8 modules that look like this. And these are comprised of straw tubes, which have got a sense wire in the middle. So when a positron goes through one of the straws, it ionizes the gas around the sense wire. The ions drift towards the wire and make a signal. And we have many, many layers of these straws so that we can look at the trajectory of the positron coming in. And this is important because from the calorimeters, you don't get very good resolution of the actual muon beam. So you know how many positrons it was emitting, but you don't know where they came from. So we need to use the trackers to do that. So here's another cartoon of the experiment. This green line shows the muon storage region. Here's one of the calorimeters, and here are the 8 tracking modules in front of one of the calorimeters. So the muons are going to decay to positrons, which have a low radius, travel into the calorimeter, and these are going to make hits in the different layers of the tracking detectors. These are then grouped together in a process called track finding. So this is a sort of example of some hits which have been grouped together. In reality, what you have is loads and loads of hits because lots of tracks are happening, close together in time. So you have to have an algorithm which is very good at picking out these trajectories, even when you have tracks close in time. We are able to do slightly more stringent data quality with the tracks than the calorimeter because we're not using this for the final analysis. We just need to choose the good muons to get a good picture of the beam. But okay, it's still a pretty complicated part of the analysis. And then you fit between the tracks in a track fitting process. So many different experiments have tracking detectors, and you use something called a Kalman filter or a chi-squared minimization technique to fit these hits and get the trajectory of this track. And then when you know the trajectory of the track, you can extrapolate this trajectory back to where the muon decayed. So you fit between the hits and then extrapolate back to try and find what was happening here where the positron was produced. So this is what we see when we do this. So this is some tracker data as a function of time since injection. So this is literally what the muon beam looks like when you measure it with a tracking detector. So we've taken our track, we've extrapolated it back, and we're building up a beam profile in the muon storage region. And what you can see is that the beam is not just staying in one place. This is because of all those things I showed on that busy slide at the start. What we have to do to try and get it in the ring is sort of squeeze it and try and make sure that it stays in this quite small region. And all of these things mean that the beam is oscillating both radially and vertically. Sometimes we call it breathing because it's kind of going in and out like that. And it's oscillating in a number of different ways. And it's really important that we can accurately measure these different oscillations. And we also have to tune the operating conditions of the experiment to make sure that none of these oscillations is at the same frequency as the one we're trying to measure, because otherwise we wouldn't be able to isolate that frequency. So the tracking detectors are really important in understanding what's going on. And also with movies like this, it's really obvious if one of your subsystems breaks, which did happen in run 1, and some of the oscillations went crazy. So it's a really useful diagnostic tool as well as important for the measurement. So all of these oscillations that we measure actually have to be incorporated into the final fit function. So I mentioned before that when we do this fit to this oscillation, we just fit 5 parameters, we fit an exponential decay and this cosine oscillation. But if we only did that fit and extracted omega A, we would not have a very good fit. And actually, if we take an FFT, a fast Fourier transform of the difference between the fit and the data, you would still see lots of frequencies in this plot. So this is a good indication that you haven't incorporated everything in the data in your fit function. So what we need to do is measure other parameters and include those in the fit to try and reduce these and make sure that we've accurately extracted omega A. So instead of fitting 5 parameters, what we actually end up fitting is 27 different parameters, and all of the terms in this full 27 parameter fit are associated with different beam oscillations. So I won't describe all of them, but you can see that when we take account of all of these different oscillations, as compared to the simple fit function, there are no residuals in our FFT, and we've got a very good sort of fit, so the way that we evaluate whether we've done the fit correctly, works very nicely when we include all of these different parameters. So we need to measure all of these using the tracker data, and actually we need to use simulation to accurately account for some of them. So that's a large part of the analysis as well. I think some of the team at Cockcroft and Daresbury were very involved in some of the beamline simulations that enabled us to determine some of these parameters. So just fitting this thing to try and extract this frequency, which you would think that you could almost do by eye, involves 8 different analysis teams, 19 different analysis methods, and what all of these teams do is, as well as the data being blinded, they all set different offsets that they don't know what each other's analysing, so that they're all doing these analyses completely independently. And then there's a procedure at the end where they'll all compare their results and make sure that they've that all their results are consistent before we remove the final blind. So this is a really complicated analysis, as you can probably tell from this function. Okay, so now I get to the title of the talk after that rather long introduction. So what are the computing requirements that enable us to analyse this high statistics data set? So here is a plot showing the accumulation of data over the time that it's been running. So the g-2 experiment switched on in full in 2018. I moved out to Fermilab at the end of this time, but I was already there doing my PhD. And then the result that we released in 2021 was just this data in the red here for run 1. The result that we announced in the summer this year was run 2 and 3. So the total value that we've got out now is the combination of all of these 3. But actually all the data that we've accumulated so far is all the rest of it. So we're up at nearly 350 billion decay positrons that are analysed in our plots. So this has surpassed the proposal goal of the number of statistics we needed to accumulate. And really the reason we just have to do this is because we're a statistically dominated experiment. The largest systematic uncertainty in our measurement is statistical. So just by counting more muons, we can reduce the largest uncertainty on the measurement. So this is what's the analysis for this part is underway now. And this plot on the right-hand axis here just shows the target uncertainty when we've analysed this number of positrons. So the statistical precision we expect to reduce by a further factor of 2 when we've analysed the rest of all this data set. Okay, so 334.5 billion positrons approximately. How do we analyse these? So I wanted to share with you this paper by a colleague of mine, Paolo, from a conference where he talks about a small experiment, big data. So 180 collaborators in a particle physics experiment is actually quite small compared to LHCb or other LHC experiments, which might have many thousands of people. But that doesn't mean that our data volumes are very small. So he called it small experiment, big data. And he goes through all of the stage of all of how we begin to analyse all this data. So I'll go through some of these steps now, but it involves the Fermilab grid centre and different types of ways of processing data. So I'll just talk you through some of the statistics about the data in the experiment. So as I said, we've got 24 calorimeters, 54 crystals per calo. Each one of those is coupled to a silicon photomultiplier, which is provides the signal that we digitize. So that's 1,296 channels in total, and these are sampled at a rate of 800 megahertz. And in addition to that, we've got 2 tracker stations with 8 modules each, 108 and 128 channels per module, so that's 2,048 channels there, and these are sampled at 400 megahertz. So what we call an event in our data acquisition is one stored bunch lasting 700 microseconds. So for the calorimeters, we digitize a waveform lasting that long and see which positrons appeared in that time. An average muon performs 4,500 orbits during this time. We get about 2,000 hits in all the calorimeters during a bunch, and there are 16 bunches every 1.4 seconds from the accelerator. So these are just some stats for you, but it basically means that once we group all of the data from all of these systems, what we need to collect is 2 gigabytes every 8 seconds, basically. So that's the rate of data that we're collecting. So per day, we're taking 12,000 subruns, total of 24 terabytes. We can't really just park this on a PC in the experimental hall. We've got to do something a bit more sophisticated to handle all this. The total size of all of the data in the whole experiment, we've got more than 10 to the 11 high energy positrons corresponding to 7 petabytes of raw data. So the data is stored on tape. I really like this part because there really is a tape robot that drives around and gets your data and injects it into a computer when you're ready to analyze it. So all of the experiments of Fermilab and probably CERN will store data for long time storage on tape. And then when you want to read it, it's staged to a read pool prior to the production. So the raw files are staged, and then we analyze them using the Fermilab grid. And then the produced files are transferred back to tape once the analysis and reconstruction and everything's done. So then, if you wanted to look at the analysed and reconstructed data, you would then stage new tape to look at that data. So this is a really non-trivial task to produce and handle more than 7 petabytes of raw data, which accounts to 4.5 million files. So I think this counts as big data for your seminar. So all of the data contribute to the measurement and have to be reconstructed. So we can't throw any of it out before the reconstruction stage, because if a positron came from the ring and entered our calorimeter, we want to know about that positron. We may throw things out later if there are certain data quality conditions that we then realise, something wasn't working during that time. But in principle, we have to reconstruct everything. So this is a multi-step sort of parallelized production workflow. We continuously sort of automate the staging of the data from tape to disk. We sort of as continuously as possible running 5,000 jobs on the grid and doing the first stage of analysis, which is calibrations for the detectors and performing preliminary validation plots and data quality selection. And this is a whole collaboration effort. So everyone in the collaboration, I think probably Katie might have taken some of these production shifts. Everyone has to sit down and just check how this data collecting is going and making sure that the parallelization jobs haven't stopped and things like that. So this is just a snapshot from Paolo's thesis, actually showing the number of files per day that get analysed by the collaboration. And this is for run 2, 3, and 4. I think for 5 and 6, we got even better, and we're producing even more files per day. So this plot here just shows the number of raw files that have been analysed over time. So I won't go into all of the different lines, but you can kind of see where different problems were happening, or we weren't staging the data, but eventually we end up with like millions and millions of files that we've analysed over the whole time. And the total amount is 4.5 million files of raw data that need to be analysed. But all the data has been produced and reconstructed and is now ready for the final analysis. So this is the fitting of those wiggle plots that I showed. So it's a really big milestone to have all the reconstructed data ready. And now the collaboration is just going through the actual physics analysis step. But yeah, I do follow that link to Paolo's paper if you're interested in the requirements for handling data volumes of this size, because he goes into a lot more of the details. Okay, so just to summarise, the analysis of runs 4 to 6 is underway, and we expect to publish this value, the final measurement of g-2, by approximately 2026, depending how it goes, but it seems to be going okay so far. All of the data production is complete. The final data set is 3 times larger than the run 1, 2, 3 statistics, and the total uncertainty of the run 1, 2, 3 that we published this year is 0.2 parts per million. And we aim to reduce the statistical uncertainty by a factor of 2 with the full statistics, with the target final precision with the systematics uncertainties as well of 140 parts per billion, or 0.14 ppm. Again, there's loads of work on the theory side to confirm the standard model value. So it's kind of out of the scope of this talk, but there's a lot of the groups at Liverpool, so Graziano's group and Katie's working on it. Confirming the standard model value of g-2 is now a huge priority, both for theorists and for experimentalists, because we want to know the significance of our measurement. Everyone's very proud of having measured such a precise quantity, but we would like to know if it's a signal of new physics or not. So there's a new experiment called Muon, and there's reanalysis of data from other E+ E- experiments that's going on here at Liverpool and internationally to try and shore up this standard model prediction. And I think that they expect to update the standard model white paper value on a similar timescale to our experiment. But some of these checks will go sort of a decade into the future, because, if you want to be really sure that these things are correct. So it's good to have multiple different ways of calculating them. So far from throwing a spanner in the works, we actually appreciate that the lattice community is doing this, because it keeps things nice and interesting. Okay, so thank you very much for listening and attending, and hopefully I didn't bombard you with too many physics statistics, but please let me know if there's any questions.
Okay, so we'll start with questions in the room.
It says on Zoom, but
yeah.
okay, just seeing as you pointed at me, the data you're taking and reanalyzing, Are you doing the track fits once, or are you sort of repeating them with better alignment calibrations multiple times? Is it sort of what's the chain of analysis? Do you sort of do let's take some data, let's do a preliminary analysis, let's calibrate things, let's reanalyze with better calibrations, and that goes around several times, or is it just once?
So,
Sorry, I wonder if you could briefly repeat the question for people online.
Oh.
If we're using the one in the ceiling, they should all be able to hear. That
Yeah.
big panel, it should be the microphone. I don't know.
did everyone hear?
We were able to hear it quite well, so don't worry about repeating it.
Okay, great. Yes, good question. So for the tracking, no, we sort of aim to do it once, but we do then end up repeating it. So the first time we did it, we just sort of take the data and analyze it and do the track fitting, and it was sort of fine. Now that we have more statistics and that we're doing other analyses that I didn't mention, such as the search for Muon EDM, which is sensitive to the number of tracks that you have. So you want people are going to go back and reanalyze the tracker data now that we sort of understand other ways of doing it a bit better. But there's no sort of automated procedure for retracking. The tracking that we do once is the tracking that we use, but we do end up repeating it. So we actually use the UK grid as well as the Fermilab one to do the reprocessing of the tracking. But yeah, the standard analysis procedure is just to do the fit once, if that makes sense.
Any questions from anybody else in the room?
It's G-2. So you know how we had old results from the certain experiments, and I'm saying at some point that we got rid of them because you know they're like sort of outdated. Are we going to do that with the Brookhaven ones at any point, or are they still like they're okay? Maybe like say if we do like another G-2, then they be outdated.
Yeah, so you think you've stumbled on a political question, but I think so. There's different ways of presenting our results. So if I just get back to this, for run one we quoted, and here in fact we quote the experiment average, which does include the Brookhaven one. So the Fermilab ones are in red, the Brookhaven ones in blue, and then the experiment average is with the combination. Statistically, eventually we won't really need to include it, and the fact that it's sort of consistent will mean that whether we can include it or not won't actually affect the value that much by the time we're at the final data set. But whether we publish the legacy result including that one or not, I think that we'll probably publish just the Fermilab number, and then it's up to whoever combines these things, the PDG or something, whether they include it. But yeah, I think for now, just because of this, so I didn't really go through all the history of the experiment, but that's quite interesting too. So the magnet that we use, for anyone that doesn't know, is exactly the same magnet that was used for the Brookhaven experiment, and they moved that from Brookhaven to Fermilab to perform this experiment. So in that sense, it's kind of the same experiment in a way, because the magnet's such a large part of the experiment. So in some sense, it does make sense to keep them combined. But yeah, statistically, I don't think it will matter whether we include it or not in the final one when we've got the full statistics.
Any other questions? I had a brief kind of non-scientific one.
Yeah.
So can you talk about maybe some of the challenges that you have? So obviously this is, small experiment, but very complicated, lots of different technical challenges. How do you kind of make sure that everyone's on track? How do you make sure that different groups are aware of what everyone else is doing? Are they aware of what everyone else is doing? How do you kind of communicate results and conclusions internally? How does the whole kind of collaboration process work, I guess?
Oh yeah, that's a good question. So now it looks a little bit different than it did at the very beginning, just because we realized on the way the best way to organize everything. But yes, basically the collaboration is run a little bit like a company. We have different sort of departments or groups, and we all report back to each other at a weekly meeting, and then we have every 3 months we have collaboration meetings where we go into sort of report the news from the previous 3 months and go into all the details. But there is basically like an organizational structure. So we'll have the spokespeople, and then 1 or 2 actually analysis coordinators, who then there'll be analysis coordinators of each individual analysis. So the magnetic field part, the wiggle fitting part, like the production team was one part, there are different strands like that. They're all coordinated by like a leader who will report back to the main analysis convener. and then we have regular weekly meetings about the schedule there. So what we try and do, and we're trying to do at the moment because we just started a new phase of analysis, is come up with a plan and a timeline at the beginning of any analysis periods with milestones and say, okay, by Christmas, we'd like to have a preliminary run through of the data, and then, let's do that. And then you never look at the original timeline you made at the end. But that's the idea, is that you try and have a timeline and stick to it that way. But yes, it's very I like the G-2 collaboration because having about 200 people in total and then actually actively working on it all the time, it's even less people than that. Once you're in your little groups, it's sort of, you get to know everybody.
Yeah.
So when we had this in Liverpool, this was everyone that came, and there were some people on Zoom, but everyone knows each other really well. So the communication works really effectively between all of the teams. But it is a really large effort to make sure that all these different things are on track. So something that happened was the data production. So these guys did such a good job because they're the first bit. And if the data production slows down, then everyone is affected. Yeah. And this is also the bit that kind of costs money, because we have to, these resources are basically bought from Fermilab, so we have to buy these wood slots effectively. So we can't just be wasting these resources and making sure that we get everything produced on time. It is very difficult. So those guys have a really big challenge, but we just report back regularly. And so the collaboration did respond, because initially there weren't enough people on this team doing these shifts, and it was really a large burden of work on them. So in the last 2 runs, or maybe 3, they started making all of the collaboration take offline shifts. Whereas for run 1, all of this stuff was just done by 5 people. So it was good that we updated that. Yeah, but it's a good question.
Great, thank you. So I see that we've got Debdeep who's got his hand up. So what if you want to go ahead with your question, Debdeep?
Hi, thanks, Alex. Hi, Saskia, thanks for this nice talk. I have a small question from the first part of your talk, regarding the straw tube tracker. So what are the fill do? Basically, I guess some mixture with argon and CO2 or ethane or something like that, or some other gas?
Are you a straw tracking expert?
Yeah.
Okay. Yes. Where are the trackers? They are filled with argon ethane. Where is my tracker got? Yes.
Yeah.
So originally we were going to use argon CO2. So
yeah, they have this in Panda, argon CO2, for example.
Yes.
Mm-hmm.
I have read Panda documentation. So we were going to use argon CO2, and then we needed to be able to put the HV up a bit higher to be able to have the threshold that we needed. So we had to upgrade to argon ethane. So it's a little bit more tricky running with ethane because it's flammable, but for the requirements of the gas mixture that we needed, ethane allowed us to go to a higher voltage on the wires.
Yeah, okay. Mm-hmm.
So I think for anyone that doesn't know about straw tracking detectors, the reason you have 2 is one of the gases, the argon, will be the gas which gets ionized and produces the signal, and the CO2 or the ethane that we're talking about is something called a quench gas. So it's kind of technical, but it just stops an avalanche effect of all these things being produced. So we have to the voltage you can run your detector at depends on the gas choice for that quench gas. So thank you, great question.
Thank you.
So we've got a couple of questions in the chat potentially, so I'll pretend to be them unless you a question.
Okay.
Okay, there's no questions.
Oh.
We can hear, thanks for the talk. Okay.
Oh, thank you.
I was going to ask, when you switch to ethane, do you get polymerization? Because back in the oldie days on LEP, one of the issues was if you put hydrocarbons in your detector, it eventually turns into sort of glue plastic and destroys your wires because it coats them and then they break.
No, but that is just based on the fact that they're all still in there and working. So I don't know if eventually you would be, or if the rate means that we just haven't reached that level yet or something. So we kind of ended up running the g-2 experiment. How long's it been? 5 or 6 years. And originally we thought it was only going to be 3 years to take all of the data. So we kind of knew that these modules wouldn't have an infinite lifetime, and I suppose that the aging would get worse if you ran it for a lot longer. But because we thought it was going to be so short, we didn't do very vigorous aging studies actually. But it hasn't been a problem. The operation of them has been totally fine. The only thing that started to go towards the end was the vacuum seal on some of the detectors, but the polymerization didn't seem to be a problem.
Okay, I know in the past people have put deliberately hydrofluoric acid in, or at least they put in fluorine, which purely to clean out the hydrocarbons that were building up on the wires.
Yeah.
So other experiments have had that as a problem, but it depends on the exact mix and how hard you're hammering it.
Yeah, and maybe we're just it's low enough that it's okay, I guess.
But I guess you also then had to, as soon as you put a flammable gas in a cavern, you get a whole other set of safety rules.
Yeah, so again, there could probably be a whole talk about the chain of filtration for the gas system. Wouldn't be very interesting, but that was a big, it's that definitely. So when we needed to switch to argon ethane, that was actually decided a little bit late in the day, and that was a big deal at Fermilab to do that. So yeah.
Great. Any last questions? Anyone in the room?
Okay. Just want to ask a naive question, which is, okay, I understand why you need to keep all the data. So then if you have to keep all the data, then do you apply, or do you know if you apply any compression to the data, or do you store it all?
Oh, it is compressed. Yeah, yeah. But that 7 petabytes is the compressed volume. Yeah.
Anyone online have a final question? If not, then we'll thank our speaker again.
Thank you very much.
Right, so those of us who are here in the room now got the opportunity to go to the pub. Anyone online who wants to go have a drink, please feel free. Thanks very much for joining, and we'll be back next month talking about neural nets in the context of nuclear magnetic resonance. So hopefully see you all there.